Welcome to my new calculus channel. My name is John Gabriel. And in this lecture, which is lecture 11, we'll be looking at the new calculus derivative and how it's defined and how to use it. So in advance, I apologize for the quality of this video, but it's free software and it's easy to use, and I can record as long as I like. So, in the previous chapters, we covered how mainstreamers think of their derivative, how they defined it, and the flaws and the problems with rigor. And we also covered the very important concepts of number, arithmetic mean, and we also saw proofs, constructive proofs, the first in human history, of the mean value theorem, using both the old calculus, or the flawed calculus, and the new calculus, which is the one that I formulated. I really actually discovered it because well-formed knowledge is never invented. It's only discovered. So let's begin without further ado. Excuse me. The derivative in the new calculus is the slope of a tangent line that is defined as follows. So what do all these things mean here? Okay. First of all, let's just read the definition quickly. It's just a short paragraph. It says, where m and n are horizontal distances from the point of tangency, that point, x and f of x, to the endpoints of a secant line that is parallel to the tangent line at the same point, at this point. And x lies between x minus m and x plus m. And in the diagram, this is what it means. So we always find the slope of the tangent line using a parallel secant, okay? So this is a parallel secant in red, and in light blue or cyan colored is the tangent line. This here is the horizontal distance, m, and the horizontal distance, n. And those are the endpoints of the secant, okay? Now, when I first was studying Newton's calculus, his bogus calculus, and nothing made sense, this didn't come to me right away. I had reached a period in my life where I was incredibly frustrated, and I almost gave up. And I thought to myself, well, look, if I give up now, then all the previous hours that I spent will have gone to waste, and in reality, I would have accomplished nothing. So it dawned on me that these concepts had to come right from the beginning. In other words, right from the time of the ancient Greeks. For example, I mean, they were the first ones to define a tangent line, and it wasn't defined as a line that crosses a curve at any point, ever, by the way. The most important feature of a tangent line is that it meets a curve in one point, extends to both sides of that point, and crosses it nowhere. The conclusion of that is that you cannot have a derivative at any point of inflection because there is no complete tangent line there, okay? And there is no such thing as a half tangent. Now, while you can use this new calculus definition to find a general derivative, even at a point of inflection, the new calculus is more rigorous and more strict. It doesn't allow for nonsense such as derivatives at inflection points. Now, and it's consistent. You will not have a derivative for the cubic function at x is equal to 0, or for a function which has a derivative that's not defined at a certain point, and according to the false ideas of mainstream, has a vertical tangent line there. Okay, so you don't get those inconsistencies in the new calculus. That's probably about the main difference in terms of results. So the new calculus is rigorous. Your bogus calculus or Newton's calculus is not. Okay, and Newton obviously didn't know what he was doing. He was simply just experimenting, taking secant lines or chords and just getting them closer and closer and closer to this point, and noticing that the closer it got, obviously the slope would get closer to that of the tangent. But he had no systematic way, neither did Cauchy, and neither did Weierstrass. Weierstrass basically just took Cauchy's rot and put it into first order logic, and that was supposedly the rigorization of calculus. Absolute rot. You still do not have a systematic way in your bogus calculus of finding the derivative. The first principles method is an absolute joke. Did you get that? It's a joke. It's absolute nonsense. And your orangutan professors of mathematics and all the morons that came before me didn't have the intellectual ability to realize that. I do, and I have, and I'm revealing these things to the lot of you morons. Okay, now, hopefully you won't be morons for too long. So let's just look at some of the ideas that led up to this. Now, first of all, I told myself, I veered off on a tangent a little bit there. I told myself that if I stop now, then I'm not going to find the answers. And so naturally, I went back to the very beginning, which are Euclid's Elements, Apollonius's Conics, and the works of Archimedes, which, by the way, a lot of mainstream professors today would need many, many months of study because they would not understand the concepts in the works of Archimedes. So at any rate, I had to find out for myself what the Elements was all about. I did not accept the ideas or the nonsense that was blurted out by my educators who knew far less than I did and did not possess even a tenth of my intelligence. At any rate, I began studying the Elements, and eventually I stumbled onto this, Book 5, Proposition 12. Now, this is one of the most meaty propositions, or the most important propositions in the whole Book of Elements. It's a proposition about all the theory of fractions. Can you believe that? That's right. Everything that has to do with the operations of arithmetic, the binary operations of arithmetic, and how to manipulate fractions, and everything that has to do eventually with the way you work with numbers, except that in Book 5 and Proposition 12, a number had not been defined yet by Euclid. So these are all stated in terms of magnitudes, and all the operations could be done geometrically. I will put a link to this applet in the details section so you can play. In fact, I'll put a link to all of them. Now, so I studied this, and I realized that what was happening here and where Euclid got these ideas was from the geometry of similar triangles. Okay? And this is what it means. It means that if you, for example, take this side divided by this side here, this side here divided by that side, this blue side divided by this blue side, then it's essentially the same as taking the sum of those, the sum of this blue side, okay, sum of these blue sides, and dividing it by the sum of these blue sides. It's really not that hard to see. I'll also put a link to this, and you can see that it's true. And this will work for any similar set of similar triangles, not only a right triangle as I have shown you here, okay? and we'll see some more examples in a moment. And also, I showed you that I don't have to put numbers here, by the way, and this identity would still be true in terms of the magnitudes. Algebra came into play when we decided how to call these magnitudes, okay? Algebra deals with the measure of these magnitudes or lines, right? Now, let's leave that alone for a second and go to the next applet. And the very first one I showed you not so long ago was this one here, right? These are the same similar triangles that I was showing you earlier, right? Can you see I'm actually calculating the derivative here, calculating the derivative of this function, okay? And the derivative is this value here, 1.245 at this point, okay? See that, right? And I'm showing you how rigorous this is. Now, of course, you cannot put this point over that one because then m and n are 0, and there is no secant line with the pair 0, 0. In other words, with m equal to 0, the distance m equal to 0, and the distance n is equal to 0. That's not possible. Then there is no secant line. So m plus n can never be 0. That's one of the wonderful things about this. And it always works because what's left over, this expression here in x, m, and n, is always equal to 0. And you can find innumerably many values, m and n, such that this is equal to 0. Just take any one of these parallel secant lines. Take one of those, take the endpoints, and plug it into the expression for q, x, m, n, and it'll give you 0, even before you reduce this difference quotient or after. So this here is the definition of the new calculus derivative. Now, I stated it like this, but you could also have on the side here plus q, x, m, and n, because it's equal to 0 anyway. So ultimately, it would be f prime of x is equal to f prime of x plus q, x, m, n. That means once you've gotten a term, which is the derivative, and the rest are all equal to 0, then you can express it in the way that I express it here, okay? So you could say it's equal to f prime of x plus q. You could say f prime of x is equal to f prime of x plus q, x, m, n. All right? Now, so as you can see, this similar triangle is exactly the same as the one I showed you in here. All right? Exactly the same concept. So it turns out that if Newton had actually bothered to study the elements, he might have realized that this was a solution to the tangent line problem thousands of years before he came along. Okay. Now, let's leave that alone and let's see another example. This example here is with a cubic. And again, it's the same story. This k, by the way, must always be equal to f prime of x, because k is the slope of this tangent line. And it doesn't matter how you do that, okay? See, these similar triangles here, this little small one and this one, will always give you the correct value, okay? No matter where you are. You can move that all along like that, and it will always be correct. And just to see this generally, I made this as a demonstration here. You can move it anywhere along a curve and it'll work because there are the similar triangles. See that? So the problem has been solved by me, the great John Gabriel. Okay. I will also put a link to that applet and all applets that I've shown you right now. Let's continue with this chapter. So now, I said this definition can also be written as follows, and I've just explained that to you. In other words, where I had a k in the applet, all right, this particular part here. See where I had this k plus? That's the same as f prime of x. All right. So This expression is obtained if every factor m plus n is cancelled from the numerator and denominator of the finite difference quotient, of this finite difference quotient. And it is comprised of any combination in m and n, right, which may or may not contain x. And it is also very easy to prove that m plus n is a real factor of every term in the numerator. So from the definition, this is true, yes, from the definition. Now, m plus n is a factor of the left-hand side. Therefore, it is also a factor of the right-hand side. And it's only possible for it to be a factor of the right-hand side if it divides every term of the right-hand side. So we know then that m plus n is a factor of both sides and every term on the right-hand side. Okay, so from the point of tangency, it is possible to construct any number of similar triangles whose one side is a parallel secant line. This fact is true for any function that is continuous and smooth. And by the way, you mainstream morons do make that assumption when you mess around with your bogus derivative, your bogus limit with your derivative definition. You make the assumption that it's continuous and smooth everywhere in the interval that contains the point that you're actually considering the derivative. The only exception is if the given point is a point of inflection, in which case a tangent line is not possible and hence a derivative is meaningless. A derivative is the slope of a special kind of straight line, one that is tangent to another curve. No straight line can be tangent to another straight line. So while every straight line has a slope or a gradient, not every straight line has a derivative. It's only a derivative if it is tangent to another curve at that point. Just as I mentioned to you in the last lecture, a graph or a function doesn't have slope at every point. There is no slope. The slope is defined as the gradient of the tangent line at that point, okay? Because the only geometric object that can have a slope is a straight line. No other object can have a slope. In the diagram that follows, two similar triangles are shown, but innumerably many such triangles are possible. And I've already shown you this. I give you a little explanation here of what happens as you've seen in the applet. Okay. And I discuss all the objections by the mainstream moron academics. How do you know if a parallel secant line to any given tangent line is possible? Well, thanks again to my ancestors, the ancient Greeks, we can safely assume that there are innumerably many secant lines that are parallel to the tangent line, and also innumerably many secant lines that are not parallel. And this was proved by Euclid over 2,300 years ago. It's very simple. It says that given any straight line and a point not on that straight line, we can draw or construct a parallel line through that point to the straight line. Why can't we use the same approach in mainstream calculus? Good question. Very, very simple answer. Since the tangent line slope, f prime of x plus qx, comma h does not depend on h, the sum of all the terms in h must be 0, because the expression f prime of x plus h must be equal to this, and which is the slope of the tangent line. This is only possible if h is equal to 0. In the new calculus, it's true that q of x mn is always 0, and it doesn't rely on a secant line that is not parallel, all right? So we know that parallel secant lines have the same slope, but none of the secant lines in the mainstream calculus ever have the same slope, okay? So the statement must be equal to f of x is clearly untrue and impossible, in fact. Not only untrue, it's impossible. Well, they imply each other. Now, f prime of x plus h is never equal to the slope of the tangent line, which in the words of Anders Kaysorg, that idiot who I had a debate with from MIT, is absolutely not allowed. And you can read my Quora debate with Anders on Quora. Where else, obviously. But doesn't the new calculus method still use limits? No, because first of all, those parallel secant lines are fixed and nothing approaches anything else. It is impossible for a parallel secant line ever to coincide with a tangent line. For if hypothetically it did so, then the secant line would degenerate into a point which cannot have a slope. As I showed you earlier in the applet, there is no mn pair 0, 0, which can be used in the definition of the parallel line slope. For this reason, there is never division by 0, because the difference quotient is valid only if m plus n is greater than 0. Both of them have to be greater than 0, not just one of them, both of them. How do you know there is a term without m or n in it? For two reasons. F prime of x does not depend on m or x. It's the same as k, which is the slope of the straight line. It is easily proved that m plus n is a factor of every term in the numerator. And I go through the proof here again, explaining to you this is only possible if the sum of all the terms in m and n are 0. And so the next question is also relevant. It says, why is it the case that setting all the terms in m and n to 0 is equivalent to obtaining the derivative f prime of x? Because the auxiliary expression given by this is always 0, no matter which m-n parallel secant line pair is being used. Did you get that? Okay. Remember I showed you here. This expression here is always 0 because we simply put the m distance in there and the n distance, and there are many of them. Look how many different m-n's there are. All right. We just put it in there. We don't put m-n 0 because then that would be a point. The secant line has degenerated into a point, and points do not have slopes, okay? And this finite difference quotient becomes meaningless. Right, so now the new calculus derivative works for every continuous and smooth function. And I give you an example here of how to find the derivative of the cubic, right? And I also show you how this auxiliary equation here, this is the auxiliary equation here, is always equal to 0, and that opens up a whole new field or theory of knowledge which has never been realized before me. And the things you can do with this have never been imagined by you because you're simply just too stupid. And nobody before me was able to realize these things, which is not surprising. But anyway, this expression here is equal to 0 and is known as the auxiliary equation in the new calculus. So given any two of these, you can find the other one. Usually you're given x, and you can pick one of m and n and then form an equation to find the other. And that's what I do here. I show you how to find m from x and n, and how to find n from x and m. And there are many uses of this equation, and it literally would require a whole book dedicated to this topic. So I just go straight into a couple of examples. So I give an example with the sine function, and I show you how to differentiate it. By the way, these series here were obtained by Newton without calculus. But in the new calculus, you can actually obtain them using the Gabriel polynomial, which is a closed form polynomial, always a closed form polynomial, and you can express any of the functions, such as sine, cos, or e to the x, or logarithm, or any other function. You can express it using the Gabriel polynomial. That would be too advanced for most of your peanut brains, but don't worry, I will give you some examples in one of the lectures that follow. It's, I think, the second last lecture. So in the meantime, let's just focus on this. Now, there are some professors, by the way, such as Professor Jack Hazinger. He's a Harvard alumnus. David Joyce, that idiot who wrote Euclid's Elements at Clark University. Many others, Anders K-Sorg. So those are three I can think of who don't understand that every trigonometric series that you see here takes only radians. This x here can only be expressed in radians, right? Did you get that, you morons? In other words, what that means is if you're going to want to find the sine of 60 degrees, you first have to convert the degrees into radians and then plug it in here. Because if you put sine 60 in there, just like that, this function will return the sine of 60 radians, not 60 degrees. Did you get that, baboons? Right. Well, I'm saying this especially for those incorrigible idiots like the ones I've just described. So you can use, these are partial sum series, by the way, because there's no such thing as an infinite series. And I think I discussed this earlier. An infinite series is a myth. This here is a partial sum series. Just adding an ellipsis doesn't make it an infinite series. And this here is never actually equal to the value sine x because it's indeterminate, all right? So now, only in certain special cases, like for example, if you can plug in a 0 in the x, then, perhaps you'll find, you're able to find a rational number. So in this case here, you would get sine of 0 is 0 and cos of 0 is 1. And that's very easy to see. Now, so I give you the derivation here and I show you how you can get it. And I go along and I show you how you can find an auxiliary equation. And I do that over here. Okay. So this is the auxiliary equation. Given any two of the x, m, and n, you can find the third. And I find one such pair, but there are infinitely many or innumerably many. And you can find them using any iterative method because the majority of you morons know Newton's root method. That's the one I used in this little C program to demonstrate how to find the roots. So you can basically go along and do that. Now, I've only given you 2 examples here in this book, but it's not necessary to give more because it's very easy for any high school student to take the derivative definition and find the answer for any particular function that you're trying to calculate the derivative. This knowledge can be learned in a matter of a few weeks, between 2 to 4 weeks if you already have a high school education, or maybe 2 to 3 months if you already know the basics of algebra, geometry, and trigonometry. You don't have to spend years becoming a master at all that bogus theory of limits, which is totally unnecessary. You don't have to take a course in real analysis, which is that topic about a mythical object called a real number, right? So, and there are much, much more things that you can do with the new calculus than you can do with your bogus calculus. So, and of course you can do everything with the new calculus that you are able to do with the mainstream calculus, but much more again. So now I think that's pretty much it. Excuse me, I'm very tired and I can't breathe properly. So that will be it for this lecture. I hope you've enjoyed it. And I hope you'll join me again next time for another interesting lecture. I don't have many left to complete the ebook, which link you can find it in the details section also. This is a new calculus channel. I'm the great John Gabriel. Goodbye, my friends.